Okay, this is a very quick demo illustrating how you can use Agentic PyMOL to do meaningful structural analysis just with natural plain language. Okay, so to start, I've got my Claude Code session on the left here. Fetch me the human cGAS structure bound to DNA. So cGAS is a DNA binding protein, so let's load this up. We can see the monomeric form bound to DNA. We see the characteristic zinc ion that's found here and ATP. So this all happened just with a natural language prompt. Let's continue this. I'm sort of interested in the APO configuration, so without it being bound to DNA. Load up the equivalent APO form and align it. Okay, and it's being brought out of view, so I want to say orient the camera so that I can see it. Okay, cool. So it's successfully aligned the apo and holo forms together. There are some kind of interesting structural differences, like you can see this kinked helix breaking here in the bound form, whereas it's just sort of kinked but still contiguous in the apo form. Find all of the residue contacts to DNA in the holoform and present as a table. Okay, Claude is finished here. We've got this table with all of the different residues that are taking part in the binding. I think it would be a little more convincing if it illustrated them in like maybe a stick visualization. So let's do that. In fact, look, it says color the contact residues red and show as sticks. So I'm just going to press tab and enter, almost like it read my mind there. Okay, so we've got our result here, and clearly it seems to have done this correctly. You can quite clearly see that the residues are occurring proximal to the DNA. And something that's sort of actually unique about cGAS is this binding activation loop. So it's a little bit unclear here, but in the apo form, there's this loose structure that actually sterically clashes with the DNA. And upon binding, you get this elongated beta strand followed by this, let's see if I can get there, this little tiny alpha helix that's shown here. But you don't see that at all in the apo form. So I wonder if it can successfully identify this region by looking at local RMSD in the alpha carbons. Using a structural alignment, find the activation loop and highlight it in both apo and holo form. Remove the red highlights and stick representations. It's remove the red regions. Okay, it thinks it's found something, so let's take a look and verify. In fact, it did find it. In pink, you can see the sterically clashing apo unstructured loop. And then in gold, it's highlighted the elongated beta strand followed by this short alpha helix segment. We can also ask Claude more interpretive questions, although I would put less weight on their accuracy. For example, we could ask, what residues help solidify, / stabilize the activation loop in its holoform? Okay, so Claude has spit out quite a few takes. I'm not sure if these are accurate or not. One recurring theme I'm seeing is that there is this tyrosine at positions 214 and 215, as well as the histidine at 217, that it seems to be making some sort of tripod in the activated loop in the bound form. So let's like visualize this. In fact, yeah, we can just autocomplete. Color these stabilizing residues and show them as sticks. So let's go ahead and do that. Okay, it's colored a little bit more than I can really interpret here. Okay, this looks a lot cleaner. I'm going to zoom in and just take a look here. Okay, so what I'm seeing is that this helical segment holds both of the tyrosines, which in the holo form are definitely oriented up towards the DNA, sort of suctioning up to it. Whereas in the holo form, you can see that the orientations are wildly different, pointing down in this case and really pointing away from the DNA in this case as well. So I think there's definitely some sort of stabilizing that's happening with these two tyrosines. They seem essential for this interaction with the DNA.